Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. For centuries, gravity has stood as one of the universe's great pillars. Steady, fundamental, unquestioned. From Newton's famous apple to Einstein's cosmic fabric of spacetime, gravity seemed like a universal law, etched into the very core of reality. But tonight, prepare yourself for a stunning twist in physics. Gravity may not be fundamental at all. Instead, it might emerge from deeper, hidden quantum processes that underlie everything we know about the universe. At the heart of this revolutionary idea is new research from physicists at Aalto University, who have proposed a radical quantum theory of gravity. One that could rewrite textbooks and fundamentally alter how we understand the universe itself. In a paper making waves across the scientific community, the researchers introduce a concept called the space-time dimension field. It sounds exotic, because it is. This mysterious field acts like a hidden bridge connecting two great realms of physics. Quantum mechanics, which governs tiny particles and forces, and general relativity, Einstein's brilliant description of gravity, and the fabric of space-time. Until now, physicists have struggled mightily to reconcile these two incredibly successful but incompatible theories. General relativity beautifully explains gravity's role in shaping planets, stars, and galaxies. But it falters when confronted with the bizarre quantum world of subatomic particles, probability, and entanglement. Quantum mechanics, on the other hand, offers stunning precision when predicting particle behavior, yet has stubbornly refused to integrate gravity as one of its fundamental forces. It's a mismatch scientists call the quantum gravity puzzle, arguably the biggest unsolved mystery in physics. This new theory boldly suggests that gravity might actually be an emergent phenomenon, not fundamental itself, but rather arising naturally out of deeper quantum interactions. Just as temperature emerges from the motion of countless molecules, gravity may emerge from microscopic interactions between quantum particles and fields. The key player here is the space-time dimension field, a completely new idea that suggests the number of dimensions we experience might itself fluctuate or shift on microscopic quantum scales. As these dimensions ripple subtly at the quantum level, gravity emerges as a measurable macroscopic effect, a consequence rather than a primary force. This idea isn't entirely out of nowhere. It aligns closely with existing theoretical concepts like entropic gravity, which views gravity as a thermodynamic phenomenon, and induced gravity, where gravitational fields appear spontaneously due to quantum field interaction. But never before have these ideas been packaged into such a coherent, testable framework. The implications of this research are enormous. If gravity is emergent, it would transform our understanding of cosmic phenomena we thought we knew well. Take black holes, for instance. For decades, physicists have wrestled with singularities, points where gravity becomes infinitely strong and our physics equations completely break down. An emergent gravity model could offer new tools to unravel these enigmatic regions, perhaps removing singularities altogether by showing gravity as a derived effect rather than an intrinsic one. It could also dramatically reshape cosmology and our theories about the early universe. Currently, scientists struggle to describe conditions immediately after the Big Bang, an environment dominated by extreme density, heat, and gravity. An emergent model of gravity might finally allow physicists to peer past the cosmic veil, revealing the true quantum structure underlying the universe's earliest moments. Oh, perhaps most tantalizingly, this theory might open a path toward the ultimate dream of physics, a unified theory of everything. Physicists have spent lifetimes seeking a single elegant framework that integrates gravity, electromagnetism, and the strong and weak nuclear forces under one coherent set of principles. By treating gravity as an emergent property rather than fundamental, this new quantum approach could finally provide the missing puzzle piece. Of course, Like all revolutionary scientific theories, this one faces enormous scrutiny and hurdles. It remains theoretical, awaiting experimental validation and rigorous testing. Physicists will need to devise clever new experiments, perhaps involving particle accelerators, ultra-sensitive gravitational wave detectors, or even laboratory simulations of quantum spacetime, to probe and challenge its prediction. But initial reactions from the scientific community have been electrifying. Experts describe the theory as compelling, bold, and potentially revolutionary. While cautioning that further research is vital, many acknowledge this idea might represent the first genuinely new perspective on gravity, since Einstein first unveiled general relativity over a century ago. Imagine a future where gravity isn't just a force to be accepted, but a phenomenon we can manipulate, engineer, or even exploit through a deeper quantum understanding. Technologies that seem purely speculative today, like artificial gravity fields or precise gravitational shielding, might become realistic goals if gravity is shown to emerge from quantum interactions we can control. Yet, beyond futuristic tech or scientific achievement, what truly excites scientists is the profound shift in perspective this theory offers. It challenges the very idea of fundamental forces, inviting physicists, and all of us, to re-examine our assumptions about the universe's most basic properties. It nudges us to wonder, if gravity itself isn't fundamental, what else might we still misunderstand about the cosmic stage we inhabit? In the years ahead, experiments at particle accelerators like CERN's Large Hadron Collider, space-based observatories, and new quantum experiments will put this provocative theory to the test. Scientists worldwide will race to uncover evidence either supporting or refuting the idea of emergent gravity. Either way, physics stands on the threshold of thrilling new insights. Tonight, you've glimpsed a vision of the universe radically different from the one we thought we knew. A universe where gravity is no longer a fundamental force, but a quantum emergent phenomenon, born from deeper interactions we're just beginning to glimpse. Whether this theory survives experimental testing or not, it's already done its job, forcing us to think bigger, deeper, and bolder about the cosmos. And that's the beauty of science itself. No matter how well we think we know our universe, it always finds new ways to surprise us, challenge us, and inspire us to reach for deeper truths hidden beneath the fabric of space-time itself.